I will talk about of lab 4 of power system, that is 3-phase synchronous generators. For the first one, there is 2 parts of the synchronous generators. First, with load, and the second one with no load. Okay, for the first part is the basic principle of operation for alternators is quite simple and can be explained using the simplified single phase alternator shown in figure 6.1. An electromagnet creates a magnetic field in the rotor. The electromagnet rotor is coupled to a source of mechanical power, such as a water turbine, to make it rotate. As a result, a continually changing magnetic flux links the stator winding and induce an alternating voltage across the stator winding, as shown in figure. The stator winding conductors in synchronous generators are usually wound in such a way that the induced voltage has a sinusoidal waveform. The stator in 3-phase generators is provided with 3 windings located at 120 degrees from one another. For the second part is, since the induced voltage are proportional to the rate of change of magnetic flux linking stator winding, one can easily deduce that the faster the rotors turn, the higher the amplitude of the induced voltage. In brief, the amplitude of the voltage produced by a 3-phase synchronous generator is proportional to the strength of the rotor electromagnet and rotation speed. There is a direct relationship between the speed of the rotor and the frequency of the voltage induced across each stator winding of a synchronous generator. For the formula is F equal to N over 60. Because since speed is usually expressed in revolution per minute, the equation relating the speed rotation to the frequency of the voltage produced by synchronous generator. However, each stator winding in large synchronous generator usually has several north and south poles instead of a just single pair. The frequency of a generator, regardless of the pair of north and south poles, is determined by simplifying the speed and the previous equation.
So I will continue with the experiment in this lab. So before that, I would like to summarize the procedure. In this lab, we consists of 3 parts. The first part is we will set up the figure like 6.2 to appropriate the setting of the equipment. Here is our figure 6.2 for the synchronous generator coupled to a prime mover. So the second part, with the same connection, we will vary the speed and the field current that observed. We will observe the effect the no load operation of a 3-phase synchronous generator. And the last one, with a same connection but adding the load. Let me see the figure. Here is it. Adding the R1. R1 is a 3 resistor section of the resistive load module in a parallel to implant of a resistor R1. So this is our third part. Right. So I would like to continue. So for the first part, we will continue with doing a connection of a figure 6.2. There is a synchronous generator coupled to a prime mover. So we are using LVSIM of EMS workstation to doing this experiment. So here we are. I'm already done the connection before, but I will conduct and explain roughly about this. So we will start with a power supply. power supply that connected to the I3 for the current, then continue to the synchronous generator following to the neutral of the power supply. So here is our power supply. Power supply is connected to the I3 here. As you can see here, I3, the output of I3 connect to the synchronous generator here. So then after synchronous generator, return to the neutral of the power supply. So we are done for this connection. So we will continue for the prime mover. The prime mover is an easy one. T to the T of the prime mover. T stand for torque and N stand for the speed. We see here the speed is connected to the T of the data equation interface. Data equation interface is function for this that to give the data output. So here the function of it, and to the speed of the prime mover. So we done with this prime mover. Then we continue with a synchronous generator. As you can see here, E1, E2, E3 is connected parallel. So firstly, connect it for the E1, E2 and E3. Same goes to the winding, then connect to winding of the synchronous generator, then to the E1 of here. Here is the connection. So then for the E1 positive to the synchronous generator, same goes to the E2 and the E3. We see here E1 of the positive connect to the positive or the winding, positive of E2 connect to here, and E3 to the this. So let's be done with this part. Alright, next, before I forget, I would like to remind others that we should to connect this power supply to the prime mover and also the data equation to give a supply. Here we go. The switch turn on and the green light will appropriate that data equation is give a voltage, so it will be function. Last but not least, before I forget, from the figure we see here, this is connected to synchronizer to the prime mover. The timing that I will show you how to do. Just click to the synchronizer, then drag to the prime mover. So we're done. Thank you. So taking back, press the front panel back. So here is it. Turn on the power switch, so the prime mover will start running. So that's all for the part 1.
So here's the question related to synchronous generator with no load operation. The first one is, are the waveform sinusoidal? The answer is yes. What is the approximate phase shift between each of the voltage waveforms? The answer is 180 degree. How do the amplitude and frequency of the voltage waveform vary when the speed of the synchronous generator is decreased? Briefly explain why. The answer is, decreasing the synchronous generator speed decrease the amplitude and frequency of the sine wave voltage. Does varying the speed of the synchronous generator affect the phase shift between the voltage waveforms? Why? The answer is, phase shift is determined by the build of the motor, so it is not affected by varying speed. How does the amplitude of the voltage waveform
vary when the field current of the synchronous generator is decreased? Briefly explain why. The answer is the amplitude of the voltage waveform produced by the three-phase synchronous generator increase as the generator field current IF decrease and vice versa, since the resistor and the supply voltage remain constant. So the voltage must be increased to compensate for the decrease in current. Therefore, the amplitude of the voltage waveform increases. Does varying the field current of the synchronous generator affect the frequency of the voltage waveform and the phase shift between the voltage waveforms? Why? The answer is varying field current of the synchronous generator and phase shift is a set value determined when the generator is built.
So I will continue with the last part. It is characteristic of synchronous generator. For this part, we are using a same connection but add resistor as a load, then only using E1 at the synchronous generator. So I will make a connection. So I'm already done for the connection, adding a resistive load. So from the supply to the R1, then I1 is returned to the resistive load, then using a black color for the resistive load toward the synchronous generator here. Yeah, so that is simple.
Then record the voltage EO, field current IF, frequency F, and speed. Then record the follow table 6.1 based on the field current IF. Next, record the frequency of a voltage produced. First, frequency measured. Second, frequency theoretical. Briefly, explain why the relationship between the synchronous generator output EO and the field current if is nonlinear for the high value current. As the field current rises, the stator voltage increases proportionally. For most machines at about 80% of rated voltage, the curve becomes nonlinear, showing the effect of magnetic saturation. If the straight line characteristic is continued, the so-called A-gap line result. In the short circuit test, the rotor is turned at the right speed with a three-phase short circuit on the stator. As before, increasing the field current allows the plotting of the stator current versus the field current, a typical short circuit characteristic. The short circuit characteristic is a linear. The flux density in the machine is very low since the terminal voltage is zero. The air gap flux is sufficient to produce a voltage to overcome the leakage reactant drop. Follow the graph. Set the excited knob result record follow table 6.2 and 6.3 based on the field current IF and max speed. When all recorded, set the prime mover speed to 0. Then turn the power supply off.
So let's go to the question 20. Describe how the synchronous generator output voltage varies as the speed varies. So in synchronous generator, the speed of rotation of the rotor is equal to the speed of the rotation of the field at the stator. Excitation field current, the voltage is directly proportional to the speed. The rate of change is proportional to both magnitude of the flux and the speed of the generator. Thus, The voltage is directly proportional to the speed and the field current. Question 21. Describe how the frequency of the voltage produced by the synchronous generator varies as the speed varies. The frequency of the generated voltage depends upon the number of field poles and on the speed at which the field poles are rotated. One complete cycle of voltage is generated in an armature coil when a pair of field poles pass over the coil. In one revolution of the rotor, the armature coil is cut by half power north pole and half power south pole. Since one cycle is generated in an armature coil, when the pair of field poles pass over the coil, the number of cycles generated in one revolution of the rotor will be equal to the number of pairs of the poles. We can conclude that if speed increase, number of cycles covered by rotor per second increase, and the frequency also increase. So in our conclusion, in three-phase synchronous generator, it produces three sine wave voltage that are phase shift by 120 angle from each other. The decreasing of synchronous generator speed, amplitude and frequency of the sine wave voltage also decrease. The lower the field current of synchronous generator, the less the amplitude of sine wave voltage. We can conclude that the output voltage and frequency are proportional to the synchronous generator speed. That's all from me. Thank you. Assalamualaikum.